Thank you, Terence, for the introduction and for giving me the opportunity to present this work, which is a joint work with Matt Roberts, who was my PhD advisor at the University of Bath. So the plan for the talk is the following. I'm going to start with two examples that are to be thought somehow as warm-up problems. The first one is from branching Brownian motion, and it's going to be a model where the Brownian motion particles will branch at a rate which depends on their position. And this will be useful in the sense that I will also be talking in my main model about branching random walk, where the rates are spatially dependent. And so, as a reference, people that do branching systems normally think of branching Brownian motion as the first example to think of. So, we will be doing a similar thing, but for branching random walks later. And the second example is a fragmentation model with homogeneous rates. So the idea in the model that I'm going to present, which is the new part of our work, is that we're going to relate a branching random walk with a fragmentation model. And so from the branching random walk, you can go back and think of Bbm, but in terms of the fragmentation model, you might like to think of the homogeneous version of the model that I'm going to define. And then I'm going to couple the two somehow and explain an equivalence of a fragmentation model with a branching random walk. So after these two examples, I'm just defining the model we're working on, and I'm going to present our main result, which is, well, you have a system of blocks fragmenting, and you will have tons of particles at large times, and we're interested in determining how large this number is, so how fast it grows in time, and we will give an almost sure result for this number. And then, well, the last part of the talk will be about details on how we can prove this. So the proof of this result is somehow standard in its structure, so it will be mostly a second moment method plus technicalities. But the problem is that you run into a lot of traps, and so the idea is that I will give you the general structure and hopefully explain a bit here and there how you get out of these traps. So let's start with the Bbm model. So in standard Bbm, I think everybody knows it. You start with one particle at the origin, and every particle moves at branching Brownian motion. And normally, these particles will all branch at rate 1 and give birth to a number of offspring, which all perform a Brownian motion. What's different here is that the rate at which these particles branch will depend on their position. So it's going to be a constant beta times power p of the position of the particle with the absolute value. So what I'm doing is basically, well, you run your Bbm, and when particles are very far away from the origin, they're going to split faster. And when they split, okay, we allow them to have a random number of offspring with a supercritical offspring distribution, and the system behaves like the usual Brownian motion. We just change the rate. So imagine that for this model, you fix some large time, big T, so that would be the time window, and denote by nt the set of particles that have been generated and are alive at that time. So nt will be a recurrent notation in my talk, and it's just the set of particles that you see at time big T. And then what we're interested to look at is, well, I'm taking a function defined on this time window, and I want to look at the number of particles alive at time t whose path has followed this function f for all times up to time big T. So I'm just fixing a particular path and check how many particles actually follow that particular function. And if you look at the expectation, well, what you see is that this number grows exponentially, and it's going to be the difference of two terms. It's not important the exact the exact form that this rate takes. It's just to give you an idea, because it will appear later on in a similar way. So what you see is that there is an exponential growth term, which is just the rate function. So particles will split at b, and their position is near f. So this represents the growth rate along the path, and you're integrating over all your time interval. And the second term is a penalty. So in some sense, it's the cost for one particle to follow the path. So for those of you familiar with Schiller's theorem for Brownian motion, this is just a large deviation result, and it's telling you the probability that one Brownian path follows f between 0 and 80. So in the branching random walk model, we will see a functional similar to this one appearing. And what's nice is when you want to find a scaling for this number, you need to, well, this is already telling you how you should proceed. You should balance these two terms out. So what you see is you should rescale this function to a function defined on 0, 1. And the rescaling is just bit t in time and the power of t in space, the power being explicit. So if you just do the calculation, this is telling you that the expectation grows like a power of t times a functional on 0, 1, which depends on this rescaled path with the f. So, moral of this story, well, you can rescale the paths in a suitable way to get a power of t, and then there will be a functional which depends on the rescaled path, and this will tell you, at least in expectation, how the number of particles following f will look like. So this was a work that's, I mean, it's from 2015 and by Derestiki, Brunet, Harris, and Roberts. So if you want, think of this Bbm as a reference for the branching random. Yes?
Shouldn't that average also depend on epsilon model? I didn't see the...
Yeah, that's why this is an approximation.
Okay, so you're only thinking
yes.
epsilon small.
Yeah, it's small. But, so morally, if you take a ball centered at f, then this will look like the functional at f. Yeah. Okay. So let me now move to define a fragmentation process. So what we're thinking is a square fragmenting into rectangles. So the fragmentation process starts from the unit square, and every rectangle will split at a constant rate r and will split into either direction with a fixed probability. So in this model, we choose to split along the horizontal line, so the base with fixed probability p, and with probability 1 minus p along the vertical direction. And thereby, we obtain from any rectangle two smaller ones. And when you fragment in one of the two directions, you choose the point at which you fragment the rectangle uniformly along the edge. So this model has been introduced by Bolchezan and Hampley as a fragmentation model that explains how molecules rearrange in a crystal. So if you imagine a crystal undergoing some transformation, and the configuration of molecules in a crystal starts from being very ordered, so I mean, think of it as a uniform square. And then if molecules rearrange, forming smaller rectangles, you see somehow plates coming into the organization of the molecules, and that's how a fragmentation model appears. So to give the example, you start from the unit square. At rate r, you choose to split in one of the two directions. So in this case, with probability p, we've chosen to split along the base, and this point is chosen uniformly along the base. And then you keep on going, so each one of these two rectangles will split at rate r. So let's say the one on the right will split first, and we've chosen to split along the height. This happens with probability 1 minus p. And the important thing in the model is that this crack only propagates until it hits the boundary of the parent rectangle. So somehow, when you look at the behavior that happens within a rectangle, this is independent of what happens on the outside. And this will be important to give the branching property when you define an analogous branching random walk. So you can just keep on going this way until you find a complicated fragmentation of the square, and this somehow has been interesting for these authors because, well, these flat plates should resemble the way that the molecules rearrange and are therefore divided into smaller area with a symmetric structure. Right, so what are we going to do is to define an analogy between the fragmentation process and the branching random walk. So how does this work? If you think that you start from the unit square and just going to represent base and height with two dimensions, this is 1, 1. And when it splits, well, we will find the red rectangle which has dimensions u1 and 1, and well, its sister rectangle which has dimensions 1 minus u1 and 1. And if we keep on going, the children of the red rectangle will be the purple and the blue one, and because there's a split on the height, the second dimension will change, So the purple will be U1, U2, and the blue one will be U1, 1 minus U2. So every time there is a split, I'm drawing a uniform random variable, and this will indicate the new dimensions of the two children. And if we take, okay, this should be different kinds of green, but if we take a further step, then you see that there's another break on the base, and we get that one rectangle has the product of two uniform random variables and then a uniform on the height, and the complement of the uniform for its sibling rectangle. So you already see that there is somehow a tree-like structure, and if you think of this model where everything happens with constant rates, the number of splits along the base will be just a Poisson process with rate r times b, and the number of splits along the height will be a Poisson process with rate r times 1 minus b. So if I fix a specific time, I will know how many splits there have been in both directions. And, well, in both directions, I will just have a product of uniform random variables. That's telling me how the two sides of the rectangles will change. So you see that here you have a product of uniforms. You just take the log if you want. It's an analogous quantity to study. The product becomes a sum, and that's just a continuous time wrenching random walk. So this is just, I will explain this in more detail for the model with inhomogeneous rates, but if you want, just think of everything happening at constant rate and giving you this product of uniform random variables. So what do we want to do? So the definition of our model starts with a basic observation, which is, if you think of the fragmentation model, it should be intuitive to think that long and thin rectangles split faster than squares. So this is a very natural thing to say. If you think of a rock, you just throw a rock on the floor. What you will see is that, well, if you have a block which is more or less a square, that will be less likely to split than a rectangle which is very long and thin. So what we're saying is we want long and thin rectangles to split faster than squares. And intuitively, we want also to say that when they split, they're more likely to reduce the longest edge. So when a block splits, it will, well, be more likely to go back to choose smaller fragments which look more like squares than their parents. And so in order to get this, we will define two functions, a different rate function and the probability of splitting in the horizontal direction. So these two were just R and P, the two constants in the fragmentation model that I've just been talking about. And they will just give an inhomogeneous version of the previous model. So we will be looking at a rate function which is the maximum of these two ratios. So you should think that if B is equal to H, so if we have a rectangle, this will just be 1. So rectangles will split at rate 1. And whenever either B is much smaller than H or the other way around, so as long as a rectangle moves away from the square, this ratio gets much larger, and so it will break much faster than squares. And the same idea goes for the probability. So if you think that the height is much smaller than the base, then the log of the height would be large, so this probability is close to 1. And this is the probability of splitting along B. So in this case, we have a rectangle which is very long and short, and with probability close to 1, the smaller the height becomes, we will split it along the base. If B is smaller than H, so if the base is really small, then in the same way this probability will be close to 0, and so I will not choose to split along the base, but along the height. And this goes in a symmetrical way. Right, so you might wonder why this 1 minus log b appeared in this function, which makes it a bit overcomplicated. So the logs are just a technicality in the sense that I was anticipating we will take a log transform, and so this will become linear after we take a log transform. And the ones are just to make this model well defined. We will see this in the next slide. So just two final comparisons of the model with constant rates and the model that I just defined in the previous slides. So on the left, every rectangle is splitting at a constant rate 1, and we have the same probability 1/2 of choosing to split either vertically or horizontally. So these pictures have been obtained with random colors, but more or less the red should correspond to rectangles that are very thin, and green colors to rectangles that are very long and short. So you see that there's a prevalence of red and green. And in this case, you see a lot of squares appearing, and somehow yellow becomes the predominant color, which is in the middle of the red and the green. So maybe now it's a good time to show you a simulation. Okay. Not here. Yes. Sorry. Okay. So this is just a dynamical version to get to the final configuration that I was showing you in the previous slides. And well, if you just follow one very long and thin rectangle, you see that it immediately becomes a square. And we will seriously use this property that the preferred shape is the square. All right. Okay, so let's move to let's see in more detail what it means to define an equivalent branching random walks. So we will take a minus log transform. So the fragmentation process is a process of bases and heights of rectangles. And in the branching random walk, the two components will be minus the log of the base and minus the log of the height. And they will denote these two components by x and y. So the fragmentation process starts from the unit square, so 1, 1, and therefore the branching random walk will start from the origin. And well, this is just the analogy between the rate function and the splitting probability. So the green one is the one that I've been telling you about for the fragmentation process, and the one for the branching random walk can just be obtained by substituting minus log of b with x and minus log of h with y. So I'm not doing anything, just rewriting things with different variables. And the splitting probability, well, can be obtained in the same way. There will be a minus log, so there's a change of sign, which will mean that for the two components of the branching random walk, if x is small, then you're more likely to split along x, for example. So this will mean that if you have one of the two components being very close to the origin, that's going to be the preferred component along which there is a jump. And this is just, well, the opposite of saying if b is larger than h. If you invert the signs, then this is x smaller than y. So what happens to the jump is the following. When there is a jump along the base, then the rectangle BH becomes b times u and b times 1 minus u with the same height. And the rate is just going to be r times p. So for the branching random walk, what happens is if you take minus log, you will just see a jump in the first component, and the two children particles will have a new position given by the same uniform random variables, and the jumps will be minus log of u and minus log of 1 minus u. So the two children particles have correlated position, and this is just what's going to happen every time there is a branch. So I'm going to draw an independent uniform random variables, and this is the position of the two children. And this happens at rate Rx, so just R times P. So this, of course, is symmetric in Y, and from now on I will just refer to Rx and Ry to denote the two rates at which things happen in either component. So, well, the jumps, as I said, are going to be minus log of uniform random variables. And this is already one first technicality that appears, in the sense that minus log of a uniform is exponentially distributed. So you see, you're going to see exponential jumps, and that's not going to help. So that's the first technicality we have to solve. The problem with the exponential distribution is that it does not fall in the strong Raman regime. This is large deviation, kind of jargon, but what it means, it's just it will satisfy a weaker version of Raman condition, which is saying that the Laplace transform is finite. So in the strong version, this is finite for all values of lambda. for the exponential distribution is just finite for some of them. And why is that a problem? Because when we're going to rescale the paths of our branching random walk, you're going to see some macroscopic jumps after the rescaling. So if you work under the strong primary condition, the rescaled paths are continuous, but this is just a weaker condition, and so you're going to see some jumps. And this means you cannot work with, continuous functions, subnorm. This is going to be much more technical. So the function set we will consider is the set of functions on 0, 1, which are Cadillac, non-decreasing, and start from the origin. So this is just a one-dimensional, but of course our branching random walk is in dimension 2. We are starting from the origin because the branching random walk starts from the origin, and we are allowed to look at non-decreasing paths because the exponential distribution is always positive. So that is actually going to help. What are the problems that appear with non-continuous paths? Well, this was similar to the talk by Emanuel Scherzer, I think, so members from the HIM will remember. If you consider, for example, a sequence of functions which can have 2 consecutive jumps in a very short time, this sequence will not converge to what you expect, so just a function with a single jump, if you look at the scorable metric. And the reason is that however small this jump is, well, the metric is going to see it. So we cannot work with the usual scorable distance and the scorable topology. We need a weaker version of that, which is sometimes called graph topology or M2 topology in Scorpot's papers. And this will be built on a comparison between the graphs of the functions in the following sense. So it's basically the Hausdorff distance, just to mention Hausdorff again in our talks. So you're considering the graph of the functions by gluing all the jumps with a vertical segments, and this gives you a curve in R2. And you're going to look at the epsilon fattening of this curve. Then if you consider the superposition of these 2 epsilon fattenings, then they need to be close. Or if you want, as it was said in the previous talk, if you look at the superposition of the 2 graphs, the biggest error you can make needs to be smaller than epsilon. And then the distance between the 2 functions is said to be less than epsilon. So the M2 topologies, is very general, can be considered for any Cadillac paths. Because we're only looking at non-decreasing paths, it's going to be the topology induced by the Levy metric. So what the Levy metric is defined here, but it's basically saying that 2 functions are close if their graphs are close both in time and space. So it's this epsilon fattening definition. But enough for that. This is just to explain why we need to work in this unfriendly functioning space. And okay, this is our main results. Are there any questions on the definition of the model so far? Okay. So our main result, as anticipated, is a result on how many particles we have at large times. So I will denote by nt of d the set of particles in a large generation for which their rescaled path is a function in my set d. So d is a subset of these E2 Cadillac non-decreasing functions. It has 2 dimensions because our branching random walk has two components. And what I'm saying is I look at all particles alive at time t, I look at their path, I rescale it with a factor big T in both time and space, and I'm looking at which of these paths are close to a function in my set of functions. And then, well, our result is telling you how this number of particles grow. So it's stated in a large deviation kind of fashion, but it's a result which holds almost surely. And you should think about it as the number of particles in a given set growing exponentially in big T, times a functional which depends on the rescale path and on its integral up to time 1. So this is going to be very similar to what I showed you in the first slide for Bbm. It will be a different functional which plays the same role and which is written down here. Don't try to remember it. The plan for the rest part of the talk is explain how this comes up. So just be mindful for now that it's a functional that depends on the rescale path. And if you take any set, well, you need to take the supremum of this functional for all functions in the set that you chose. And you need also to condition on the functional being positive at all times. So the functional is an integral between 0, 0, and 1. And what we're asking here is that it stays positive when you're integrating for all intermediate times between 0 and 1. And the reason for this is the following. So this is a result for a number of particles, so that's going to be an integer. And what I'm saying here is that it behaves like exponential of big T times something. If that something is negative, then the number of particles drops down below 1, because it's exponential of negative power. And so, because it's an integer, it's going to be 0. So what this condition is ensuring is just at all times there will be some particles near my chosen rescale path f. If in any way this number drops down to 0, then at some point there are no particles following this lineage, and therefore there will be no particles at time 1 that have always followed that lineage. So this is just making sure that at all times there is at least one particle that is following this path. Right. So the plan for the remaining of the talk is giving you an idea of the proof. So the first thing is I'm talking about rescaled paths, and well, I don't want to take all of them. There will be some of them which do not behave nicely enough, and the first thing we can do is get rid of them. So I only want to keep some sort of good paths according to some definition, and my definition is going to be the following. It's this set Gm of all the paths, think of it for now in dimension 1, all the paths that are in this cone. So it's a cone between two straight lines, and you should think of m being a very large constant. So I can take m as large as I want, and I'm somehow looking at all paths that fall within this red area. Why are these paths nice? Well, because they're bounded above and below by two straight lines, and the rate function is essentially given by the ratio of the two components, and therefore it will be bounded. So what we're interested in showing is that we can restrict to this set of good paths, and we can get rid of all the other ones and restrict to a set where the rates are bounded. First problem, there are no particles whose rescaled paths are in Gm. And the reason is that these two straight lines both start at the origin, and well, your branching on walk starts at the origin, and for some exponential time it will stay there. So all the paths will be 0 for a while, and then you will see a jump. So I need to expand, at least for a little bit, Gm. So imagine that instead of the red area, I'm looking at this, well, the region between the dotted lines. And this is going to be my real definition of good paths. So 2 steps. First of all, we want to get rid of everything outside this nice area. So what we can show is that the probability that the rescaled paths lie outside is really small. So you will not see any paths outside this area, or you do with small probability. So we can only consider the nice paths. And what we do with that area is saying that it is totally bounded with respect to the Levi metric in this set. So in the set of paths which are actually in the red area, so really nice ones, and piecewise linear functions. So just take a very thin grid and take a piecewise linear function on that grid. You can show that Gm is totally bounded in this set of paths. Totally bounded means just I fix any radius, I can cover this area with finitely many balls around functions in this nice set. So what, sorry? Oh, okay. So what it means for our problem is if I'm looking at particles with rescaled path in any set, I can cover that set with finitely many balls around nice functions. So it will be enough to look at events of the form, well, number of particles whose rescaled path lie in a ball around a nice function. Yes?
So is it the same as saying that G square MT is compact? Or is there no sense of compactness in this?
I think compact implies totally bounded, so this should be weaker.
Okay.
Am I right? No, that's complaining. I've done this a while ago, so So we can restrict the analysis to a ball around a nice function. Then I'm going to look first at the expected number of particles whose rescale path lie in a ball around this function. And then, well, the most important tool to compute the expectations is going to be just the many-to-one lemma, which is a classical tool for branching systems. And I just want to explain here briefly how it works and why it behaves nicely when the rates depend on the spatial position of particles. So what the many-to-one lemma says is if you start from an expectation that involves all the particles in a generation big T, we can change this expectation into another one, which just involves one particle, so psi, which is going to be a spine, just an infinite line of descent. The way you change the expectation is looking at a different probability measure Q, and so your spine will branch twice as fast as particles in the original branching system. And what you find is, well, you pay a price, which is this is the expected number of particles at time t, if you want, so e to the integral of the rate function. And then you have the indicator that only the spine is near enough to your function f. So it's really reducing the problem from whatever, how many particles you have in generation t to just one infinite line of descent. That's all I want to say about many-to-one. Why does this behave nicely? Well, because the rate is going to be evaluated at the particle position, so it's random. The power of this is we end up with the indicator that the spine is close to f. And so the spine cannot be just randomly anywhere, it's going to be close to f. And so you can just do estimates on the rate and say that, well, the rate along the spine is just going to be the rate evaluated at f. And now this is deterministic, so the expectation just becomes the expected growth rate times the probability of this event, so the probability that just one spine is near f. And so, well, this is already, building up on the calculation. We will have the first exponential term, which is the exponential of the integral of the rate function, and then we need to be able to evaluate the probability that just one line of descent is near f, where now this psi is just one random walk, which branches at rate 2 are evaluated at its position. Right, so just next step will be, we will work when t is large, so how does this integral behave? It will just be e to the power t times the rescaled version of this integral, so an integral between 0, 1, which does not depend on big T anymore, and this r star is just going to be the limit as big T tends to infinity of the rate function. So this is the ratio of the two components, and as big T tends to infinity, we just see the ratio of the two components of the function in 0, 1. So, well, this is just technicalities, just to say what we end up with when t is large. And so the problem is reduced to estimating this probability, so the probability for a single random walk to be near f. So this is just, if the branching rate was constant, this is just a large deviation kind of probability. The problem is we have rates that depend on space, and so we need some extra work. What we will show is that, I have this expectation, I found the first term, and now I want to estimate this probability. This is just repeating from the previous slide. So what we find is, well, what's the rate of decay of this probability, and it's going to be functional just depending on f. I want to comment on this, so on the form that this functional takes. So again, imagine that the rate is constant and you have exponential 1 jumps. Then the usual large deviation result for random walks would tell you that the rate of decay of this probability is, well, this integral with the constant rate minus the derivative of the function plus its singular component. And this is a result that you can find in a series of papers by Nowotsky. So, what form does our functional take? If you look at it, well, it's just two identical lines, one for the x component and one for the y component. And each one of them is just a repetition of this integral with a rate that depends on the position of the part. So you're integrating, replacing r with 2r of x for the x component and 2r of y for the y component. And other than that, they're basically identical. So this is a very intuitive generalization if you think of it. It's just replacing a constant rate with the integral over the rate evaluated at that particular position in time. So how do we prove this? This is one of the most technical parts of the work, and it's essentially a coupling idea. So if you think of the rate being, well, a rate evaluated somewhere near this function, what you can do is looking at a small interval I and saying, well, I'm gonna trap this process between two processes with constant rates for which I can do the estimates. And then the upper and lower bound we will have with two processes with constant rates will give you estimates on this original probability. So I'm just going to fix this small interval I, and we build a coupling between these three processes. So Z minus and Z plus are lower and upper bound, and Z of S will have the same distribution as the spine. So how are these three processes built? They all start from where the spines start. So they all start from the same position. And then, so the upper and lower bound have these rates, which are constant and are just the supremum over all the values that the rates can take in that interval and for all the functions in the ball. So where is the spine going to be? In this ball. And so the rate will be evaluated along the spine. So the biggest this rate can be is the supremum over all times and all functions in the ball, restricted to that interval. So that's the biggest, this is the smallest, and I'm going to do the same for two processes, well, y plus and y minus. So z plus is just going to be x plus and x minus, which have these two constant rates. And so z minus has two components which have rates are x minus and are y minus, and z plus has two components x plus and y plus. So the plus is being the upper bounds and the minus is being the lower bounds for x and y. So you start by defining the plus process, and the other two ones are defined like this. So the first process will just be the one that jumps the most of the three, right? So the other two will just skip some of the jumps, and they do this in the standard way. So with some probability which gives them the right distribution for the jumps. So Zs needs to jump at rate 2Rz, so it will just be this ratio, and the minus process needs to jump at rate Rx minus or Ry minus, so this is the ratio of the two. Okay, and then by construction there will be independencies between the x and the y's, and within the x's the lower bound is independent of the difference between the upper and the lower bound. This will just be properties of the coupling, and the moral of the story is that we can trap the process we want between two processes with constant rates, and this, we know how to estimate, and we'll give an upper bound on this probability or a lower bound as well. Now this form of the exponents is not important. What you just need to see is that it's already in a good shape, because this is the square root of 2 times the rate, and this is basically a difference between the endpoints at the interval, and it will be something that then gives the derivative of the function. So just the moral of the story is we can relate these exponents to the integral of the rate functions, and if we can do this, then we can ultimately estimate the probability we want, and it's going to look like the functional that I defined in my proposition. Right, so we have all the tools now to see how k appears. So the expectation for the number of particles in this ball is the growth rate, so exponential of the rate function, and then this probability was estimated by this functional j. So the sum of the two will give the final answer for the number of particles that follow F. So again, you see that there is a growth term, which explains for the number of particles that are born along the path of F. And J will be the penalty term, so the cost for a branching random walk, just a single trajectory to follow the function F. And so that's the K that appeared in my main theorem. So how do you conclude the proof? Well, this was a result for a fixed T, right? I'm looking at the expected number of particles at time big T that have done something for all their paths. And now what you want to look at is, well, for all times large enough. So how do you get that? You have the upper bound is basically done. You have the result for a fixed T. You can just use Markov's inequality to show you that the probability that this number of particles is too large decays exponentially. And the way you conclude the proof is by some Borel-Cantelli arguments. You can take a sequence of times, and then you need to show that in between these times nothing too crazy happens. So I mean, it's not a short proof, but it works. And for the lower bound, we have more technicalities. So normally in the lower bound, you have a general strategy when you're working with branching systems, which is you just augment the probabilities by letting the system run for a while. Because what do you gain? If you look at a fixed generation, nu times big T, where I'm thinking of nu being small, what I can show is that there are a lot of particles at that generation, and that number can be big with big T. And then, well, each one of these particles is going to generate an independent copy of my original tree. So if I look at all the descendants of particles in this early generation, so I'm just saying particles of time big T that are children of one of the particles in this early generation, and I'm looking at how, well, these particles stay near F. Then, well, if all particles at time t, well, if the number of particles at time t is small, then this needs to happen for all the descendants of all particles at time nu t. So it will just give the product of the probability that well, the same thing happens for all the descendants of particles alive at this generation. So it's just saying I can look at one of these copies, so I can just look at the tree starting from a particle in this generation, and then all these probabilities, well, all these events are independent and they get the product of the probabilities. So the strategy to show that this probability is small is the following. You show that if you look at this number of descendants, if you fix U at an early generation, and you look at the number of descendants that follow F, you show that there is a strictly positive probability that this number is small enough. So the event here is the complement. So what this is giving you is that each one of these probabilities will be smaller than 1 minus gamma. 1 minus gamma is strictly smaller than 1. And then you show that the number of terms in the product is large. So this will give you, well, the upper bound here is a number smaller than 1 to some power that goes to infinity with t, and so you go. So now I need to restrict these two steps, showing that the number of descendants of a particle staying near F is large enough, and then showing that I actually have enough particles in an early generation. So for the first part, well, what you can do is a stacking moment method. So this is standard, you just have a lower bound which depends on first and second moment. So what's the trouble? You need to calculate the second moment. So the expected number of particles squared. And this you can do with the many-to-2 lemma. So if you remember what I did with many-to-1, I just had the expectation here and I could transform it into an expectation just involving one spine. What you can do with many-to-2 is you can do the same but with 2 spines. And this will be 2 particles that start together and then at some point separate and have independent paths. Just let me briefly mention that you can do this with k moments. So this is a very, very general result by Harris and Roberts. So you can compute the k moments, translating the expectations into expectations that only involve k correlated paths. So for example, this is the 7th moment. So you start with all the spines following the same path, and then at some point, some of them decide to follow, well, one child path, and some of them separate. And so this will give a system of, well, k correlated paths. So the first part is in common to all the spines and so on. So you need to be careful of how they're correlated, but still it's much simpler because you do not have just a k moment, but k paths, which you can control much better. So this is just the ingredient to compute this probability, and everything works out here. The main problem is actually step 2, which is showing that at small times you have a large enough number of particles. And what's the problem? You're working when t is large. So let's think of how the rate function looks like when t is large. So when t is large, you get this limit, but because you start at the origin, you have a discontinuity. And so it's not clear at all how particles should branch when they're close to the origin. So what you can do is you need to be very careful and construct a path along which it's easy to control how many particles you have. So this path for me will be h. So, okay, what do I want to do? I'm trying to look at how many particles follow f. I have no idea how they behave at the start. So I'm going to define a path h, which changes f near the origin, and then at some point is glued to f, right? This all happens at small times, so in the big picture it won't matter. So how do I define h? H is going to be a piecewise linear function, which is also good, so it's the nicest function I can think of. And it behaves like this. So up to a really small times, it's just two straight lines with drift a half. A half not being important, the important thing, the drifts need to be identical. So what am I actually doing here? H has two identical components. So if you think of the fragmentation, so this means that the two components are identical. So this is going to be a square. So what I'm asking is that a lot of particles follow H, but because of my definition, a square is a preferred shape. So I mean, this intuitively is telling me that it will work. I will be able to show that a lot of particles are squares, right? And then, well, because we wanted to switch back to f, which is the function that I chose, and I want to show that there are particles near f, well, h is going to change gradually, so it's a piecewise linear function whose drift adapts to the drift of f, and from some time onwards it will just be equal to f. So first path, just make sure that h is, well, what I really want, what I really need to show that there are a lot of particles. So at the end of this, at time mu prime times big T, I will have tons of particles there. And then we can control how these particles follow H when the gradient changes. And ultimately, all this flow of particles will be near F at time, well, mu. So the main difficulties you have in building H is just not the definition, is that it needs to be well behaved. So what I ultimately want is that this number of particles that follow, well, F is near the number of particles that follow H. And I want it to be close to K evaluated at F. So I need to make sure that by changing the function to H, I'm not losing much. So the two functionals are actually close. Forget what this means because it's really complicated. And another thing I have to make sure is that the functional around H stays positive at all times. This is just the requirement that was in the theorem, and it's essential to say that, well, there is positive probability of finding particles that follow H. So the question is, how do you change the drift of H to get to F? Because 1/2 is not going to be a problem, it's just on a very small interval. The question is, how do you change the drift so that the two functionals are close and such that K is positive? And this is, it's a very nice trick. So what you can show, well, is summarized in this picture. So lambda mu is going to be, one value, possible value that the drift of F takes at small times. So think of it to be the derivative of F at the origin. So what we know is that the functional K evaluated at F is positive at all times. So I can only restrict to functions F for which the functional is positive. So the set of lambda and mu which is possible is given by this green and orange area. So what you want to show is that, so this is again, the picture is the set of possible drifts. So you want to start from lambda mu, so the drift of f, and trace it back to 1/2 and 1/2, which is the drift I'm starting from, in such a way that you never get out of this area, which is the area where the functional is positive. So what we can show is that you can always find such a path. So for any drift that f has, for any lambda mu such that the functional is positive, you can find a path which stays in this region, so for which k stays positive, that goes back to 1/2, 1/2. And this is going to be how you define the drift of h, so how the drift of h changes from 1/2, 1/2 to the drift of f. And this path is really nice because you can find it such that it only moves horizontally or vertically or along the main diagonal. So that's going to help you when you compute and make sure that all the properties work out in the way they should. So to conclude with, this is open problems. So if you remember the Bbm model that I defined at the start, so that also gives you a functional that tells you how the number of particles increase, right? For any set of functions. So now I'm saying I want to choose a particular set of functions. Let's say I choose functions that end at z. So I'm going to look at particles that, well, follow any path which ends at z. So this is just fixing the endpoint at time big, well, in the scale picture, so the endpoint will be z times big T. And I want to know how many particles end up there. So by the result we have, this is just going to be the supremum over all functions that end at z of our functional. This is free from the theorem we have. I'm just choosing a particular set of functions, those ending at z. So the number of particles that end at z is the supremum of this. And why are we interested in that? Well, if you think of the fragmentation model again, this would mean that you fix a specific shape, so a base and height, and I'm asking how many rectangles have that base and height at some large time, right? So if you want to determine this number, what you have to do is optimizing this function, right? So you need to find the supremum. And, well, a really nice result is that this answer is known for the Bbm model that I started with. And it also has a really nice interpretation. So for the Bbm, the authors could show that this supremum, well, the optimization problem, has a unique solution, which is in blue in this picture, and also has a really nice interpretation. So the red path is the rightmost part of the Bbm, which is known, the curve is known. And our solutions are the blue ones, so they follow the rightmost path up to some point, some optimal point, and then they move away. But while moving away, they solve the second order ODE. And it's really nice because it's very explicit and it also has a meaning, like following the rightmost particle and then move away. And well, this is an open question for our branching random walk. It's, I mean, the good thing about Bbm is that it has continuous paths, you work with the soft norm, and so, well, this is very complicated already to show, but at least you're working in a nicer setting. And for us, we do not have an analytical result, and also we had some clues on the solutions, and all our clues proved to be wrong with some simulations. So it is really open, and if you have suggestions, I'm really interested in hearing more about this. And with this, I will conclude the presentation, and thank you for your attention.